Good day, everyone, and welcome to our discussion about total internal reflection. Have you seen a mirage? Why there are mirages? If you try to look downwards into a pond or river to see if there are any fish there, your view may be spoiled by light reflected image of the sky or of yourself rather than what is in the water. On a sunny day, reflected light from windows or water can be a hazard to drivers. When a light ray reaches the boundary between two transparent materials, it may be refracted. If it is leaving the more dense medium, this refraction would be expected to bend the ray away from the normal as it emerges. The ray enters the block along the normal without bending by refraction. Inside the glass, the ray strikes the midpoint of the flat side. What happens next? Look at this illustration. In the first illustration, if the angle of incidence is small, most of the light emerges from the block. There is a faint reflected ray inside the glass block. The refracted ray bends away from the normal. The second illustration shows that the refracted ray emerges along and parallel to the surface of the block. Most of the light is reflected inside the block. At the critical angle, the angle of refraction is 90 degrees. We have seen that if the angle of incidence is greater than a particular value known as critical angle, the light is entirely reflected inside the glass. Look at this illustration. The third one demonstrates that at an even greater angle of incidence, all the light is reflected inside the block. No refracted ray emerges from the surface. At angles of incidence greater than the critical angle, the light is totally internally reflected. There is no refracted ray. The phenomenon is known as total internal reflection. The angle of incidence when the ray changes from just refracting to total internal reflection is called the critical angle. Why does it call total internal reflection? Total because 100% of the light is reflected. Internal because it happens inside the glass. And reflection because the ray is entirely reflected. For total internal reflection to happen, the angle of incidence of the ray must be greater than the critical angle. The critical angle depends on the material being used. For glass, it is about 42 degrees, though this depends on the composition of the glass. For water, the critical angle is greater, about 49 degrees. For diamond, the critical angle is small, about 25 degrees. Sparkling of the diamond is due to cut of diamond faces and high index of refraction, which means a very small critical angle, which is equal to 24 degrees. Incident rays can undergo multiple total internal reflection inside the diamond before exiting the top of the diamond. What do you need to know about the diamond cut? The small critical angle, which is about 25 degrees, allows the rays of light that enter a diamond very likely to be totally internally reflected. So what happened? They bounce around inside, eventually emerging from one of the diamond's cut faces. That explains why diamonds are such sparkly jewels. The cut affects the sparkling of the diamonds. An ideal cut diamond is a round, brilliant, or princess cut diamond that is cut to ideal proportions and angles has excellent polish and symmetry ratings. An ideal cut diamond reflects almost all the light that enters it and is among the rarest cuts. The ideal cut diamond is used as benchmark for grading all other diamonds. Shallow cut disperses light at the bottom. Deep cut disperses light sideways. While ideal cut diamonds are perfectly proportioned to refract light, reducing that fire in brilliance up through to the table and ground. If the angle of incidence of a ray at the surface is greater than or equal to the critical angle, it will be totally internally reflected. Critical angle and refractive index. When the angle of incidence is equal to the critical angle, the refracted bends through 90 degrees. The angle of refraction is thus 90 degrees. Substituting in the equation for Snell's law gives n is equal to sine I over sine C. Sine 90 degrees is equal to 1. So we have n is equal to 1 over sine C, or sine C is equal to 1 over n. Sample problem. Find the critical angle for diamond with a refractive index of 2.4. Substituting the value of n in the equation, sine C is equal to 1 over n gives sine C is equal to 1 divided by 2.4, and that is equal to 0.417. Finding the value of sine -1, 0.417 by pressing the second function, sine C is equal to 24.6 degrees. Exercises. Copy the questions and answer in your physics notebook. Show your solution as much as possible. Number 1. The critical angle of water is 49 degrees. If a ray of light strikes the upper surface of a pond at an angle of incidence of 45 degrees, will it be totally internally reflected? Explain your answer. Number 2. The refractive index of water is n is equal to 1.33. A. Calculate the critical angle for water. B. Using a protractor, draw an accurate ray diagram to show how a ray of light striking the internal surface of water at critical angle is refracted. 3. Which ideal cut of diamond should you buy and why? And that's the end of our lesson. This is Teacher Rose of Woodrose International School. See you next time.